So I think we'll come to the discussion here. So what we have seen in the last lecture is the input-output configuration. There is only say normal way. I have not say removed the discussion here. So the ideal way of having a measurement system is only desired signals are present. That is what we know. But in actual practice, there is one more input that is going to interfere the signals, the desired signals, and then that is also added as an output into the instrument, and the output is altered. I think we've seen some of the examples. The very simple way we try to explain. Say the initial pressure, suppose is 20. Initial temperature is suppose 20 degrees Celsius, and the same is to be measured. So output will be same. But in actual practice, because of the interfering unit, we find that there is some additional input going inside the system, and probably suppose it is of order of 0.5 degrees Celsius, then output may read 20.5, which is say numerical or say algebraic sum of the two different signals. In addition to this, there can be one more signal that is called as modifying input signals, which are going to alter the value of desired signal as well as the interfering input. Am I audible to you all? Please let me know. Yes, any one of you can answer. Am I audible to you? Yeah, I'll be very happy to hear your sound also. Actually eager to have the say interaction. But unfortunately, nobody is going to ask any question to me, neither in the chat nor in the say voicemail. So again, repeating question: am I audible to you all?
Yes, sir.
Yes, sir. You are audible.
Yeah, thank you for your nice words. After say long time after the initial lecture, first time I am hearing at least two students' voice. Thank God, I am not teaching to the. There is somebody behind the screen also. It's very matter of happiness for me that I heard the student's voice, at least. Okay, so coming back to the modifying input is the one that is going to alter the signals, the desired signal as well as the interfering signal. And if the modifying input is, say, for example, found out that is going to affect per degree Celsius rise in the temperature, say for 20 degree of input signal, it has given rise to 20.02. After modifying the input signal, it has given rise to the signal at this end, which is of the order of say 20.2 degrees Celsius. Simultaneously, that modifying input also have modified the interfering signals, interfering inputs. Say again, it is correlated with the some degrees, say per degree rise. Say it is 0.1 degree something. Then it will have the interfering input modified to 0.52. Earlier it was 0.5. So in this condition, now the output shown because the modifying input will be 20.72. If there is only interfering input present, then it is going to show suppose 20.5. But ideally, we have desired that the signal should be the order of 20 degree. It should show 20 degree only. Right. So this was the ideal one that is desired. Ideal output to be displayed was 20. Because of the interfering signal, it has shown 20.5, let us say. And because of modifying, it has altered both desired signal as well as the interfering signal, and the total output shown by the instrument or measurement system will be 20.72, say for example. So this is how the inputs are going to affect. So from the discussion itself, what we can understand is there can be the desired input, which is a very much intended, that is to be measured actually, right? But because of some uninherent factors, say some unintentional factors, we find the quantities are going to alter the input signals, and the instrument or measurement system becomes sensitive to that. So that is nothing but our interfering input. Okay. The third kind of input is the modifying input. The quantities to which the measurement system is sensitive, but it affects both the interfering as well as the desired input. It's called as a modifying input. So from that earlier example, we have come to know, or we have seen how the output is changed. Now, what is the objective behind studying this is, whenever we think of any measurement system, any desired measurement system for the given application, we must know what kind of interfering and modifying signals are going to present, and we want to eliminate those as far as possible. So our sole objective of studying this is to have minimized effect of the interfering and modifying input to the order of 0. It should be equivalent to 0. There is no effect at all of interfering and modifying is what is desired, but is not possible at all because of the many, say, situations like physical components present into the measurement instrument or measurement system, or the different say configuration, functional blocks, or the physical blocks. There are some inherent interactions going to happen in the form of interfering and the modifying input. Let us see the example for this now. So let us say the pressure measurement in a manometer. Say if it is a mercury manometer of which pressure is being measured such that the pressure is one lever of that manometer is connected to the, say, pressure P1, the other is connected to pressure P2. Now in this condition, the pressure P1 and P2 ideally is going to create the difference of the pressure, say P1 minus P2, if we consider P1 is larger, which is, say, proportional to the deflection on the scale or the scale graduations. We are going to make the marking such that it is going to be proportional. Say maybe unit pressure difference is equal to unit graduations made on the scale. So this is what is desired. So for measuring the pressure difference, let us say this is the mercury in the manometer, and this fluid 1, fluid 2, of which pressure P1 and P2 is being measured. It's very simple pressure measurement system, but in actual practice now, let us assume that this beaker or this measurement system, manometer system, is mounted on some kind of platform which can be subjected to acceleration, which may have some motion. So because of the motion, what will happen? The level will no longer remain parallel to the surface or the parallel to the, say, datum, but it will acquire some new shape, some new say orientation it will acquire. Say for example, it will have the graduation here. Now you can see that this graduation has given rise to, say, some unwanted effect here, and instead of this del x, it will show something else than what is the true input. So in this condition, we can assume that acceleration is going to act as an interfering unit. Why it is interfering? Because it has altered the input signal. Now suppose now P1 has changed to P1 dash and say P2 has changed to P2 dash. Still, there will be some proportional change in the graduation because it is not now parallel to the datum. It has taken some inclination because of acceleration, and because of this there is change. So that change has made the desired signal to change, to alter. Whatever is the input, say pressure P1, P2, or P1 dash and P2 dash, P1 double dash, P2 double dash, so on. For each and every change into the input, there will be some change in the output because of the interfering input, that's because of the acceleration. Larger the acceleration, the greater extent signals will be altered. Smaller the acceleration, if it is 0, then there will be no alteration. So this is how it is going to act as an interfering unit. So similarly now, if I use this manometer which is not parallel to the datum, or it is subjected to some position, say tilt angle at angle theta, then what is going to happen? Even without any change into pressure P1 and P2, it is going to show again something else as the value. So here in this condition, this tilt angle or say orientation of the instrument itself or the measurement system itself is going to act as a interfering input. Let us discuss first only about interfering input. So what is meaning here? Again, pressure P1 and P2 is changed to P1 dash, P2 dash, P2, P1 double dash, P2 double dash, and so on. Even if it is made equal to 0, it is going to show some kind of deflection here. So this is the condition where the pressure P1 equals to P2, or say P1 equal to 0 and P2 equal to 0. Even if there is no pressure, it is going to show this change in the datum line. So that is going to act as an interfering unit. Now let's discuss something about the modifying input. What is the modifying input? Let's assume into the system the mercury is present and the room temperature earlier say 20 degrees Celsius. Now this is change, or this instrument measurement system is taken to the temperature which is elevated, say for example 40 degrees Celsius. Then what is going to happen? There can be multiple effects of the temperature. Like the scale, if it is made up of metal, it will have linear expansion, may be very small, but definitely it is not going to show the same graduation which were there at 20 degrees Celsius. At 40 degrees Celsius, the distance and the scale will have its expansion. This is first effect. The second effect of the temperature is because of the temperature, mercury will start expanding. Also, it will have expansion of the fluid that is in the say limb 1 and limb 2. So thus the temperature is going to modify both the input that is in the form of pressure P1, P2. Because of the temperature, there will be expansion of the gas and it may have further addition, say del P1 because of temperature T, or del temperature difference del T. There will be again change in the pressure P2. P2 will change to P2 plus del P2 because of temperature difference of 20 degrees Celsius. Then same thing, it is going to act the interfering unit. Say interfering signal was the acceleration. Into this acceleration condition, if suppose temperature is changed from 20 to 40, then again it will have the similar effect on the input also. So this level will again raise. So I can show this very small line I can draw parallel to this. This is purely because of the change in the temperature. There will be change into the levels. So this is how it has modified the interfering input. Not only desired but interfering input also changed. Right. So this is how the temperature is going to act as a modifying input. Take another example. If this measurement system or measurement say devices is taken in the aeroplane or in the space or on some other place where there is little change to gravitational constant, then you find probably it will read something else than what is the ideal input given to the system. So again, gravity is also going to act as a modifying input. What is modifying input? It is going to change the desired signal as well as it is going to change the interfering signals also. Right. Let me know any doubt in understanding this. How we identify, how we analyze the system so that we can identify what are the disturbing signals, interfering signal and the modifying inputs. Now in this case, inclination is also going to act as a modifying input. This was left to be discussed. So because of the inclination, even at zero pressure, it is going to show some kind of level difference. So it is going to alter input as well as the output because the level has changed, which is not corresponding to what is the ideal level to the given input pressure. Right. So if this is clear, I think we'll be able to move ahead. So this is how we have to understand each and every measurement system that we'll be discussing in our syllabus of mechanical measurement. We must know what are the kinds of the interfering input. At least we should have thought process to identify what are the interfering inputs and what are the modifying inputs into the particular system. Then only we may think of reducing those very close to zero, or at least to make something as zero, either of the interfering or of the modifying signals. We will try to make it zero. Let me know any doubt in understanding this one. Am I audible to you? If anybody listening me. Acha, Rupesh and Anshul. Rupesh and Anshul, you are there, I think online. Then you try to ask few students, at least 15 students, to make their videos on.
Yes, sir. Yes, sir.
Right. This is what we discussed. That is what we are discussed. I am not seeing any of the students made the video on.
Yes,
Okay.
sir.
Right. And our usual method, if they are not making their videos on, we can straightaway mark them absent.
Yes, sir. Yes, sir.
Right. So I think I have seen very first face now. Let me see if anybody else has joined. 1, 2. Only 2 students have made their videos on. And let me make it very clear that minimum 75% attendance is mandatory. What about others? Only 2 students have made the videos on. Anshul and Rupesh, you see it whether they have made it on or not. If it is not made on, you can straightway give the reason and mark them absent. Correct.
Yes, sir.
So let us move on. Now let us consider one more system of measuring the strain, that is called a strain gauge device. Into the strain gauge device, the coil of a small diameter wire is mounted on some surface which is subjected to the force. Because of the force, there will be change in the length. That change in the length will be captured by this gauge wire, and then there will be change in the resistance. Then this gauge wire is connected to the Wheatstone circuit so that the input voltage applied, say EB, is going to be given at the output of your Wheatstone bridge, which will be in proportion to RG. Because of the change in the resistance, there will be some imbalance, and then that imbalance will be noted down, maybe either by adjusting through the variable resistance RC. Will be able to establish the balance, and then whatever change into RC has been made to restore the balance, we can make that equal to the amount of the strain. Or without changing RC, we will find out imbalance here, the change in the output voltage U given by this equation. So let us understand this is the change in the resistance del RG will be equal to, say, del RG will be equal to the gauge factor into the resistance of the wire into the strain. Now for the normal instance of operation, the gauge factor is already decided and resistance of wire is assumed to be remaining fairly constant. So if these two things are considered, we can find that the change in the resistance RG will be more or less proportional to the strain. That is what is ideally required to be measured, right? But due to certain elements here, the output voltage will be given by this equation. Again, this equation is same here, where the output voltage, now this will be going to remain constant. Say if I write this as K, then this will be equals to the strain into the input voltage and this relation of the wires because of the strain gauge circuit. Now if these resistances are fairly going to remain constant, again this can be considered as constant K2, so that EU will be equals to this constant K into K1. Again that is can be called as a constant K dash into strain into EB. So majorly this is now output EMF or output voltage will be proportional to the strain times the input voltage EB, right? But let us assume that there are some signals present. So for example, these are 60 Hertz AC field present nearby the instrument or near the measurement system. What is going to happen because of this say presence of the AC field? We can find that there is some unwanted signal generated because of the AC field and this gauge wire that may act as a, say, EMF generation device. So that will generate some EMF. So even if I am going to make this force equal to 0, the output voltage will be shown because of the AC field. There is some kind of induction EMF into this RA, RB, RC and the gauge wires that will be reflected in the form of EO. So it is going to act as the interfering signal. It has changed. Even if there is 0 input, it is going to show some output, right? So this is going to act as an interfering signal. So we can see that the AC field is going to act as an interfering signal. Now let us assume, again come back to this, Now let us say this measurement system is supposed to be operated at say normal temperature or standard temperature of 25 degrees Celsius. But now this measurement system is subjected to some elevation, say of suppose del T equal to 20 degree. So instead of 25 now the operating temperature is 45. So because of this 20 degree, what is going to happen? The wires that are used here, small wire, it may expand. Because of the expansion, there will be change in the length, and thus it will show some kind of strain. There will be some change in the resistance Rg. Here del Rg, because of the temperature will occur. So this change will reflect to the output EMF. So even if there is no input, there will be shown some output because of the change in the operating temperature. Similarly, there is change into the length of this bar on which this gauge wire is mounted. So because of this, what is going to happen? It will have some kind of expansion. This bar will expand, and again this will cause this gauge to take more strain. So even at zero force, it is going to show some output. So these are going to act as interfering inputs. So here we must try to understand the system that interfering signals like 60 Hz AC field as well as operating temperature is going to act as an interfering signal. Right? Any doubt in understanding how the interfering signal? There can be few more things here, but broad way, the two elements that are going to affect the desired signal directly, that we are defined as an interfering signal, can be understood here. That is 60 Hz AC field and the temperature. Say the temperature is going to make the change in the resistance and give rise to the value of EO. Even at zero force, it will show some non-zero value of the output voltage. Right. So that is say then called as an interfering signal. Then likewise there is a modifying input. Now how it is modifying? Say the change in the temperature. Change in the temperature is going to give the expansion. Let us understand this. Because of the elevation in temperature, there will be change in the length, LL of wire. So because of change in the wire length, it is going to have strain automatically captured, which is say kind of a virtual strain that is not given by the force application, but because of temperature rise. So that is going to give the EU. So it is going to act as a modifying input. So the temperature is going to act as a modifying input. Again, the modifying input here will be the change or expansion of the element. Expansion of the element of which is used for force measurement itself. Right. Say for example, if there is change in the gauge factor, because we have seen in earlier expression that the output voltage is proportional to the constant K times strain into the gauge factor. So if there is change in the into the say input EMF, that is the battery voltage, right? So even if the change in the gauge factor is going to occur, it is going to modify both interfering signal as well as the modifying the desired signal both. Similarly, there is change in the battery voltage. If the battery voltage is fluctuating, say at this type of measurement, it is saying say it is say 5.02 volt. After 5 minutes, it may come down. It will be 5.0. After another half an hour, probably it will reach to 4.5. So depending on the battery performance, your input voltage may change. And because of a change in the input, everything, the phenomena itself is, the EO itself is function of the input. So as there is a change in input, there will be change in the output, which is not going to reflect anything because of the actual strain due to the force application. So that is what is going to act as a modifying input, right? So we must understand the system and identify at least broadly what are the interfering input and what are the modifying input and how they affect the signals. Then based on this, now we try to have the different methods of getting the corrections into the interfering and modifying signals. Say again, I am iterating. What is our objective? Our objective is to see that these components are going to be the minimum possible to the extent of zero. If it is possible, we are trying to make it zero. So then there are different methods of making some kind of correction so that the system is restored to the ideal input signals only. So there is called as a method of inherent sensitivity. Most of the time this is used. There can be method of high gain feedback. method of calculator output corrections, then method of signal filtering, and then last is the method of opposing input. So these are very common and standard methods. Apart from this, if there is special instrument or measurement system is to be designed, we can think of very other devices also, other methods also. Right? But the most common and most standard methods, those are established in the literature, are mentioned here and that we are going to discuss. Again, I'm iterating that we are taking this solely from the book of E.O. Doblin. You may please go through this book and try to understand these things. This is only sample, but when we'll go for the actual measurement systems, probably that may be the questions of your quiz and the tests, home test or the say class test. That a measurement system given and you may be say at least asked to say give what are the desirable input, what are the interfering input and modifying input into the given system. Okay. Now let me know any doubt till this point. Okay, please let me know if there is doubt. We'll be able to discuss or we'll move ahead then. We'll try to move ahead.
Sir,
Right. Go ahead. What is the doubt?
when we say temperature is interfering and when we say it is modifying, means how we differentiate it?
No. Wait. We have to first analyze whether the temperature is going to act as a modifying input. We have to also think whether it is going to act as the interfering input or not. Most of the time, say into the examples also we have seen, there are some physical elements into the measurement instrument or measurement system which are sensitive to temperature. So in most of the examples that have been discussed in the textbooks, temperature act as a modifying input as well as it also act as a interfering input both. Right, because say mechanical entities, what are those entities? It is temperature, pressure, say flow rate, then it is a say volume. Say all these entities have got temperature as a very inherent sensitivity factor. Try to understand this. Take any mechanical entity, say pressure, temperature, volume, density, anything that you are going to measure. It will be highly say sensitive to temperature. So definitely the signals are going to act as an interfering input as well as modifying input if we consider temperature as a factor. So your question is how to differentiate. We need to differentiate. We think independently. What are the signals? We are having the desirable signals, we are having interfering signals, and we are having modifying signals. Right? Whether the modifying signal is altered by temperature, you try to analyze. If it is yes, you call that as the element. You also try to see whether that is going to affect the interfering signal. If you see it is both, temperature acting as the factor for both the modifying as well as the interfering signals. It's clear to you now?
Yes, sir.
Right. Our intention not to differentiate. Our intention to see whether it will affect. Now what is the next step? When we have thought that it is going to affect, then we have to think how that can be minimized. Say for example, effect of temperature, how that can be minimized on the system so that it will have minimum or zero interfering signal, minimum or zero modifying signal. That is what is our objective, sole objective. Now there are few methods. Let us try to understand those methods. Any other doubt regarding this? Input output characteristics first. Right. Then we come to the very first method of inherent sensitivity. So into the inherent sensitivity, the word itself suggests something we must use as an inherent component of the measurement system so that it is going to be insensitive to the modifying input as well as the interfering inputs. So for example, equipment can be made inherently sensitive to only and only the desired input. So wherever possible, we try to implement this scheme that it is only and only sensitive to the temperature, which is the useful entity under measurement. So this can be achieved. Say for example, in earlier case of the strain gauges, what can be done? The material having lowest coefficient of expansion alpha. If I select this material for wire, then what will happen? Even if there is change in the temperature of 20 degrees, say instead of 25 degree room temperature, now it is elevated to 45. There will be very minimal change because of the lower value of alpha, that is the linear expansion coefficient, because of change in temperature. Same thing will happen if I am going to use the material on which strain gauge is being tested. I make that material to have, or select the material so that it will have very low value of alpha. Then there will be no change or very minimal change, very negligible change into the length of the bar on which the strain gauge is mounted. So that is what is discussed here. Gauge material should be such that it will have very low possible temperature coefficient of the resistance. If it will have lower value of alpha, it will have lower value of change in the length, and thus it will have very less change in the resistance for the gauge material I am saying. Similarly, I can think of having mechanical apparatus should have low coefficient of expansion because of the lower expansion coefficient, like material called as INVAR, which is having very low value of alpha. There will not be any change in the length of the bar, and then it will not show some strain because of change in temperature, even if there is no force applied. Right. Now, the third inherent sensitivity that I can infuse into the mechanical measurement system is gauge factor of such material for strain gauge application should have low temperature variation. So that we are going to study when we will see in detail the strain gauge based say measurement devices or measurement systems, where the gauge factor of the material is to be selected properly. Right. So let us understand. Any doubt into understanding this inherent insensitivity? So let us go to the next method, that is called the method of high gain feedback. The name itself suggests that instead of an open configuration, we go for a feedback kind of configuration of the measurement system, and then we give the higher gain. We increase the signals to some extent. Let us understand this. Say I am going to measure voltage of a system or voltage of the device using motor. My connection is such that the voltage is given to the motor first. Through the motor, I am going to get a torque, and then that torque is going to be applied to the spring, so that the spring will have proportional displacement XO. This is how a small voltage measurement scheme is there. I think you might be aware this is what is also done into the voltmeters. We have got some coil that is going to rotate. Because of the change in the voltage, coil is going to rotate, and then it is going to give the deflection to the spring. Right. So this scheme, let us understand this scheme now. So my input entity's voltage is given to some motor, which is going to generate some kind of torque, and then this torque is given to the spring to give the proportional displacement XO. So this is what is called an open-ended measurement system. That is called the open loop system for measurement of the voltage EI. Now in this one, through the design, I can design the experiment, or I can design the instrument or the measurement system such that through design I can make the displacement XO can be made proportional to the voltage EI, so that XO, output voltage, equals to proportional of KMO, where K is nothing but the factor for the motor, or the mathematical function representing the motor and signal change into the motor, times the spring factor, the KSP. Now into this, what has happened? If there is some modifying input or interfering input, it is going to modify the signals because of the modifying input 1 and modifying input 2 at two different elements. It will alter the signals. So ideally, I require that, say for example 20 volt is there, that should be proportional to the displacement. What I desire is EI is proportional to the value of XO, but because of the modifying signals, this will be altered, and in that condition then it will be something else. It is the algebraic sum. So then that will be added. Then now it will be EI proportional to XO plus FM. So the R nothing but the interfering signal 1, modifying signal 1 plus modifying signal 2, IM2. So definitely this will be something else than the true input voltage. Now instead of this, what I do is I go for a closed kind of system. Say in this is our earlier system of input voltage here, EO, motor, spring, and the output. Now what I do is I tap down some output given by the system, and then I have a feedback device. Through this feedback device, it will take the output voltage. Right? The output voltage will be then, say, checked with or compared with the input signal. If it is equal to, then no signal will be given. If it is less than, the difference will be given to the device called as amplifier. Now I have added one more component here, so that because of the amplifier, now proportional signals will be changed, and then it will be given rise to, through the equation. I think we can understand this system. So earlier it is EI minus EO times Km, KO, KSP, which is equals to the output voltage. Right. So here what I can understand is the output displacement XO will be proportional to the two elements, say the factor of amplifier K motor, K spring upon 1 plus Km into say KMO into KSP into KFP. Now suppose I make this denominator, say in fact because of the feedback device and the amplifier, if I make this system to have this denominator a very large value than 1, because of this KAM or KFP, I will make this larger, so that now XO will be more or less proportional to EI. I think there is one more term here that is forgotten, into EI. It should be into EI. So because of this, because of the high gain, I have increased that signal to the large extent, and then higher signals are given inside the system, so that whatever change into a signal that has occurred because of interfering a modified signal has been reduced down to a lower extent. See, again I am able to retain this proportionality, so that the effect of the modifying signal 1, modifying signal 2, 3, 4 and so on have no effect on the output voltage. So this is how the method of high gain feedback operates. So what is the advantage of this system? That only controlling IM4, that is the thing but the feedback device, if I am going to control this signal from the feedback system, is going to work sufficiently enough to maintain the linearity or proportionality, and I can have the very accurate measurement of the input signal to the output. Faithful representation is possible because the power is supplied to the amplifier. We can have a high gain feedback, right? And the another advantage is loading effect becomes smaller. Say because of the very small input signals taken here, there is a minimal loading effect. So instrument is very free from the loading effect. But only one limitation is there is a dynamic stability is an issue. Say for example, there is a fluctuation into the input signal over the time. Say if it is going to fluctuate like this, ideally this is the desired signal, the average signal is desired like this one, but there is fluctuation. Then because of this amplifier, this fluctuation may be multiplied many times, magnified many times. So it will have a larger stabilizing time. It will not show constant reading, which is say well required for measurement. So this is one of the issue. Dynamic stability is the issue. Any doubt into understanding this, how the method of high gain feedback work? Okay, so we'll move ahead. Method of calculated output. Say very simple. We calculate the difference, or we calculate the modifying signal, extent of the modifying signal and the interfering signal. So for example, now I know the temperature change. Suppose in earlier case of strain gauge measurement, if I come to know that the temperature for which measurement system was designed of say 25 degrees Celsius, the temperature at which it is being used, suppose 65. So I can have very clearly difference of 40 degrees, and I know the value of alpha. Say using the value of alpha, I can find the expansion, say equals to L alpha into del T. This is very simple expression that we have studied somewhere in the mechanics of material, or say solid mechanics. So L alpha del T, alpha is known, del T suppose 40 degrees Celsius. So what will change the length, that I know. So because of this change in length, I can go and subtract that from the length change of the gauge wire, and then I can reduce on the strain. So whatever output is shown, that will be equals to the actual output shown minus the correction, EO correction. Now what I have done, I have calculated the output that can be corrected. So for example, in earlier case of the pressure measurement, the pressure difference measurement, if the acceleration is known or the gravitational constant is known, the ideal value that I have used for synthesizing or designing the system and at which it is actually used, if I difference is known, I can find out what can be the correction that is applied, right? So it works on the principle of estimating the interfering and modifying inputs. The secondary instrument need not to act to be say as accurate as the measuring devices under consideration. It's very important here. The normal instruments, if I find out this factor from outside, that measurement use of this system, if change is 1 degree Celsius, I will have this as this something XYZ as a correction factor. If I am going to have this kind of say information as thumb rule, I can use a very ordinary instrument. I need not to have every time very standard instrument being used, right? So it effect on the output is found out. That's what we have done here, and then we can apply the correction. So those gives the correction that can be applied to the measured output. So many times what happens, if this kind of programs are made available or some microcontrollers are used, we can automatically have the correction which is going to show you the corrected value itself. Say display, if it is showing 20 degrees in output, because of this correction, say it is saying plus 0.5, then automatically it will show 20.05 as output on the display panel. Because of the microprocessors and computer is possible. Say the example we discussed, effect of the temperature and gravity in the manometer can be controlled by using method of say calculated corrections, right? So this is a simple way. Many times we find out what can be the effect of the modifying and interfering signal, and we find out what is the correction factor. We directly add or subtract, or say we process possibly either add, subtract, divide or something, and then we get the corrected output. Any doubt in understanding the method of calculated output correction? Okay, if it is not, then we'll move up again the next element in discussion. Let us say the input filtering. Name itself suggests we are going to filter out, say interfering signal and modifying signal. We apply filter so that zero interfering signal is entering into the measurement output, zero modifying signals are entering into the system, so that there is no change into the desired as well as the interfering system because of this modifying input. Name itself suggests input filtering, right? Then there can be the method of output filtering. If it is an output given, say from the system, we have seen that the desired signals are going to enter as output here, but because of interfering signal, there is addition, algebraic addition of the signals. Presence of modifying signal, it is going to alter this desired signal, and then additional signal will come into. Because of this modifying input, it will have additional interfering input, and then it is given to the system. Then what we do is at the output we apply filter for interfering and modifying signal, so that we are going to remove those signal which are entered into. We are making it that equal to 0 or near to 0, and then output will be the one that is ideally desired. So this method of input filtering and output filtering is very simple. We are going to nullify those at the entry level or exit level at the measurement output. And any difficulty in understanding this conceptually? Now this can be applied to the different systems. Say for example, now there are systems which are going to have vibrations. Say for example, there is shaking table, and now we want to measure something on that table. So we can restrict the input that is going to act as say modifying and interfering signal. If the instrument is kept on the table, because of this spring, if the springs are used to isolate the vibrating structure and the table on which measurement is taken, we can avoid the interfering and modifying signal to enter into the system here. Our device is kept here on this table. Instead of putting directly it on the vibrating structure, we put it on some other table which is supported by means of the spring. So this kind of filter is called as a mechanical filter, which is going to filter the signals at input itself. It will not allow the interfering and modifying signal to enter into system at the very first input. Similarly, now because of the tilt, say for example the earlier pressure measurement device, if it is used on some ship or some aeroplane, then we find there is a change in the tilt angle. Then we can use this kind of gimbal support or gimbal suspension. Now the platform originally on which the instrument was kept is made to have the gimbal suspension so that it can have the movement. Say I think it is given clearly, theta 1 and theta 2 is the input, and say let us assume this as theta 1 dash and theta 2 dash are the movement at the gimbal bearing. Say this is bearing 1 and bearing 2, and this is bearing 1. So at this gimbal support, we can have a very elimination of the change in the angle theta 2 and theta 1. We can make this theta 2 as close as 0. This is called as a gimbal suspension. This is again a mechanical filter, or keeping the inclination or say orientation and position of your measurement device very much to the ideal condition. It will not allow the signals to go in. The signals theta 1 and theta 2, which are going to act as a say input signals for interfering and modifying a kind of class of the desired signal, those will be restricted to the gimbal support. Again, this is a mechanical say filter. Similarly, now you can see that the earlier example of the strain gauges, where the 60 Hz AC field was present. So to avoid or to restrict the induction of the EMF because of the AC field, we can provide a shield called as a magnetic shield. Because of this magnetic shield, it will not have any effect of this AC field on the resistance wires that are used for measuring instrument or say measuring system. So this is a magnetic shield that is again going to act as a filter. Say same thing if it is a say thermocouple, the junction 1, say J1 and junction 2. There are two junctions, and then say there is change in temperature, ambient temperature, which is going to have large fluctuation. So to avoid the effect of this, what we have done, we have provided thermal insulation to one of the junction, reference junction, so that always reference junction will be maintained at constant temperature, so that only the entity under measurement of which temperatures you taken will have the effect of the change in the output voltage on the junctions. So again, this is called as a mechanical filter, say called as thermal insulation as a mechanical filter. Okay. Then similarly, we have got this method of filtering. If the AC field is going to induce some kind of EMF into this, the RC circuit, the resistance and capacitor circuit can be added in between, so that without presence of this RC circuit, the signals have fluctuation because of the AC field in this format. After providing RC, we can find that this fluctuation has gone. It has filtered by means of the resistance and the capacitor configuration. So only strain will be indicated at the output. Right. Same thing if it is the pressure measurement. Say for example, yours is a say air compressor. Because of a reciprocating compressor, the air filled in the tank is going to have some kind of fluctuation in the pressure. So instead of having the device used, we are going to use orifice. Because this orifice, we find in without orifice, the pressure sense will be like this one, because of the constant input of the air volume inside the cylinder of your reciprocating air compressor. It will reflect here on the scale. So it will go on fluctuating. Scale will fluctuate constantly. if we are going to provide a orifice here, probably that fluctuation will be nulled out. It can be only used for measurement of the average pressure inside the tank. Right, this is again a filter, mechanical filters. Right. So I think this is what we discussed. This one method, again, you can go through the textbooks to understand this. Then I think the last one I will discuss in a minute, and then we'll stop here. Then method of opposing input. The name itself suggests, if I have got some calculated estimation of what are the input signals entering into, I will apply opposite signal to that. Say unavoidable interfering input, suppose I have quantified and I have found that is of extent some value, then opposite effect I am going to incorporate here. So the effect equal to, say, exactly opposite of these signals. The entity, suppose 0.05 is some quantity that I have found out. It is say plus 0.05, it is a positive reflection. Then what I am going to do, I will have compression of the spring, suppose, to 0.05 millimeter, and then I am going to put it into the function. So the change in the spring deflection, which was plus 0.5, as the spring is now applied with some force to have this minus value, it will have the zero effect of the interfering input. So basically I am going to apply opposing input at the interfering signals entry point of the measurement system. So same thing is done here. I think this can be discussed. See, you try to understand, this is the measurement by orifice without this system. Assume that there is no system like this, there is only orifice. Then you find that there is change in the temperature and change in the pressure of the fluid is going to affect the measurement of the flow. Flow is the entity under measurement. This flow measurement is function of the pressure difference, as well as because of the temperature and change in the pressure, there is change in the density. So there are few more factors added. So to control this, there is additional arrangement made here, that it is going to have a metering pin. Okay, I think you can go through textbook for this one, because otherwise it will take few more some time. So I think we'll restrict our discussion. I leave this to you to be taken from the textbook. Okay, if there is difficulty, let me know. We'll discuss this sometime later then. All the explanation regarding this is given in the textbook. You please go through and find out how the method of opposing input is going to operate. So in fact, what is there? We are going to have the calculations of the opposing effect similar to the earlier one, that is calculated outputs. We calculate and make the corrections by making the plus and minus value of the signal, which is nearly equal to 0, so that 0 interfering signals are entering into the system. Okay, so I think we'll restrict our discussion here. So probably I am planning to have the very first test this week, last class of this week on Friday, I think. Yes, Friday class we'll have test, class test 1, based on the portion that is I have given to you. I have given some images to you. You try to study those from the textbooks. The name of the textbook also is given. And then we'll have the questioning based on, say, identification of primary sensing element, variable conversion element, and so on. That will be test number 1. So this Friday we will have quiz, or say MCQ test number 1 based on the portion given to you. There will be one more test on the same content. I will announce that in the next week probably. Anything to be discussed? So if there is nothing to be discussed, I think we will stop here for today. Thank you for joining.